Yeah, that's quite a title. I didn't come up with that. It's a little bit wordy for even me, but basically that is kind of what this talk is going to be about. So I'll see if I can get it. No, I will not move forward. Uh-oh. It just worked a second ago. I'm having an issue here. It's not going to the next slide for some reason.
Yeah, had that sometimes.
Yes, we did.
Try logging out and logging out and logging back in, or at least disconnect the presentation and then connect again.
All right. Let's see if this works this time.
There you go. I think so.
We may have to do this every slide, it looks like, but that's all right. I can do that. Just going to take a little bit. So, as we all know, odor is one of the biggest new coming issues. Not really new coming, but it's an up and coming issue for sure, especially in our standpoints. There are many noxious odors that people report that impair property use, business operation, adverse health effects. And one of the things that I wasn't really aware of until I started doing this a few years ago is that actual frequent exposure to these high concentration levels, 3 to 5 times zero threshold, can cause some indirect and even direct health effects, such as headache, nausea, vomiting, dizziness, mental stress, etc. And I'm going to have to do this again. Okay, boy, this is going to be a heck of a slide change every time. So, as we've seen today, there's a lot of different analytical techniques out there for odor analysis, cans, bag samples, nasal rangers, odor panels, just a few. At Montrose, we chose to do a little bit more in terms of direct analytical. We chose to use a mobile proton transfer reaction time of flight mass spectrometer. This platform allows us to perform a variety of analysis from nearly any location. We can use it along fence lines, inside facilities for process leak location, neighborhoods for air quality and odor monitoring, and to map areas for odor hotspots, etc. The key to this versatility is being able to analyze almost any volatile organic or inorganic compound down to the part per trillion level. And for the study that I'm going to talk about today, I'll be talking about we coupled PTR-MS with principal component analysis due to this huge amount of data that we generated. So let me see if I can. Boy, this is going to get old quick. So just real briefly, this is the nuts and bolts of our mobile testing platform. This is the proton transfer reaction mass spectrometer. And it's supposed to have a cool little graphic here, but it's not going. Uh-oh. Oops, I jumped. So as you can see on the screen, water comes into this hollowed cathode inlet. It generates ions. You can see the VOC sample comes in at the air inlet, reacts with the ions, transfers the reagent ion to the VOC, then it goes to the mass spectrometer. All this happens instantaneously and continuously. At present, we can take sample rates up to about half a second, so we can get a data set every half a second. And one of the great things about this is we can change the reagent ions because there are certain compounds that will react with water but they won't or won't react with water. They'll only react with oxygen ions or won't react with oxygen, only NO ions. So we can kind of change that on the fly as we're going, depending on what we're looking for. And we found this to be a really powerful tool for real-time analysis of odor-causing compounds. And we use this to trace these odor plumes throughout the community. So I'm going to see if this works again. Ooh, there we go. So in our odor investigation process, these are the general steps we're using to address odor issues that our clients have. We either obtain samples from the facility or we perform on-site sampling with the PTR to determine what the actual compounds are in the odor plume. And when we do this, we call this fingerprinting. And this can be dependent upon the number of sources that you have. For most smaller facilities, it's somewhere between 10 to 15 unique individual processes or steps of the process that may have a significantly chemically different fingerprint that we can use to do this mapping with. So then after the fingerprinting, we send this data to another analytical company that I'll talk about a little bit later to develop a fingerprint model. We'll take the lab, we'll move around at different locations in accordance with the wind parameters and odor complaints that we received, and we'll sample where to determine where these odors are coming from. Now, in most cases, in these industrial areas, you don't have just one analytical process. There's multiple, or I'm sorry, one facility process. There's multiple facilities with that different odor plumes, and we can use this to identify which ones come from which facility. So let's step that up a bit. So one of the ones that we initially started was in the city of Milpitas, and this was with Jacobs Engineering. I know many of you know Bart and Scott, and this is all part of a multiple research project. So we were looking to characterize the odor-causing compounds present in the San Francisco Bay Area and Milpitas area. It's received thousands of odor complaints from residents, schools, and businesses that are in the area. And these are the work steps that that were described above and we implemented during this program. So we conduct the literature search for compounds, we collected bags, we analyzed the bags, we sent the results to the principal component analysis company, and then we actually performed live sampling there at the facility. So this is just kind of a brief set of pictures here for what it looks like for those of you who may have never been into some of these lovely facilities. We did a landfill, a wastewater treatment plant, a waste food to energy, and then we found an actual force source which is the Dan Fernando estuary of the Bay Area in San Francisco. So these top three are, we were actually up on the working face of a landfill. We were right inside the wastewater treatment facility. That's about as close as you can get to the decomposing food piles. And then some of these other pictures show some of the Jacobs people and some of the other areas where we actually sampled. This bottom one, kind of a little funny story about the bottom picture. This was an unknown source. We were driving through the estuary area, and the driver knocked on the window because I was sitting in the back of this van back here, so I can't really see what's going on. And he said, "There's a terrible odor out here." And about a minute later, it finally made its way into me, and I smelled it. So we stopped to get out and look and see what it was. As we were walking over towards the area, we got about right here, and the smell changed up, came up off the water, and we both got sick. I mean, it both made us sick. It was so strong. So odors can produce some pretty powerful reactions. So I understand why there's a lot of complaints. So, we have this really powerful analytical tool for odor analysis, but what does it really look like? What are we really generating when we're moving through the lab or analyzing these sample bags? Well, this is an actual graphical representation of one of our overnight sampling runs, and I'll just talk about this one because we did 12 or 15 different locations throughout the city, but this is just one here. So, this is simplified. So I pulled out some of the compounds that make up a typical odor plume. So on the first one here, you can see there's a major contributor is acetaldehyde. And this is the actual graph for acetaldehyde. And I believe this was almost 24 hours, close to it there, maybe 21, 20, so hours overnight. So long sampling run times here as it's set there. And then if you dig into this a little bit deeper, you'll see another contributor is acetic acid. There's some acetic acid. You could see, I will let you know that right in this area around 11 o'clock, midnight, there is a wind shift. So you can see that we start seeing some more stuff later. That's common, especially in these coastal areas. But I do want to note that even though, you're just seeing this, these are very low levels. These are concentrations in parts per billion. And some of these compounds are actually below the odor threshold. So even though we can see them on the instrument face, you can't see them. We can't smell them when you're outside. So this is, you don't even have to have the odor plume present for us to determine the compounds that are really there. So there's a little bit more that's going on. This slide represents 2,3-dihydrofuran. And the bottom slide is a summation of multiple compounds that were just a small part of this specific odor plume. There are hundreds of compounds that are being measured simultaneously in real time. And it's really like the layers of onion from before. So these are truly complex systems that are not static, as you can see from the different time frames. So they're constantly changing. So these graphs that you see here is just one small step. This is a tremendous amount of data that we generated over this 2-week time period. So we really needed to do something with it. So now we're going to step into the next area, which is taking this data and performing a multivariate analysis. And it's a statistical, I'll read you the wiki definition, and then it's multivariate statistics, and is a subdivision of statistics encompassing the simultaneous observation and analysis of more than one outcome variable. In other words, because I'm not a mathematician, it's relationships between independent variables and how they relate to each other. So really, it's looking at ratios between compounds, between the source, ratios between ratios of compounds, and ratios to ratios. I mean, it just goes on and on and on and on. And it really is a really sophisticated tool to really dig into huge data sets, find similarities, and then find differences. And then, we can use this to generate these fingerprint models that we're talking about. We can apply these models out into the community. And then we can actually bin these results from each specific air sample and assign them to the facility that the fingerprints came from. So the modeling was done using 7 to 15 different dimensions of mathematics, which I can barely handle 4 dimensions, let alone 7 to 15, but as you can see, it's pretty sophisticated. But really what we're looking at here is there enough material here that is unique and represents a specific source very accurately, or is there just a lot of the same compounds everywhere and we're not going to be able to use this? So you can see there's good clustering of compounds for each individual bags, which is what these little dots are here. And I'm sorry for the picture, it's kind of small and hard to see, but these represent individual fingerprint bags that were taken throughout the facilities and how well they cluster together. So for us, that's good. There's good separations from each different bag, which means that each fingerprint has a unique series of ratios of compounds that can be used to model future results. So it took quite a while to build this model, and over a year's worth of sampling from different times of the years, because things change with different temperatures. But we put all these together and came up with these models. And so now we're going to take those overnight results that I was talking about before and apply some of these modeling values to see what really happens. So one of the locations we set out and tested overnight was at a Hampton Inn hotel. They were nice enough to let us park there and test. So I kind of broke this down into different chunks here, just because it was just too much data for the system to handle all at once. So During the first part of the sampling program, which is over here in this model, these 4 different facilities, the wastewater, the recycling, the food composter, and the estuary. I won't tell you which facility is which up here, but those are the 4 that we're looking at. So collecting the data, running the data through the models that Sartorius came up with, we find that 89% of the odor from this plume during this time frame can be attributed to facility B. 10% to facility C. We did have some we couldn't, assign to each classes, and this happens throughout the, during the whole time frame. For the next 4 hours, you see it drop down a little bit from 90 to 9. 100% of the facilities odors were met back to these facilities during this time frame with the heavy wind, and then it's basically 100% there too. So the biggest takeaway from this, and we did this for however many sources we did, I can't remember now. It was a lot of data, multiple locations. We binned it, we checked it, and there are some other results that I'm omitting just for time's sake that actually correlate to shows that this is actual statistically accurate what we're doing here and legally defensible. But the biggest takeaway is now we've developed a way to determine which facility is responsible for odors in a multi-facility environment. And I mean, this can also be applied to other things too. Fence line, if facilities share common fence lines or adjacent to each other, you can determine which emissions are coming from which facility. This applies to any other kind of compound you can measure. This has ramifications in benzene fence line monitoring, which we've used here. I'm in the Houston area. We've used this extensively there to determine which facilities are responsible for benzene across multiple fence lines, HCN, ethylene oxide. It goes on and on. So
Steve,
the next step.
Running low on time. Can you kind of wrap
This
it up
is it.
to leave a little question?
Yep, this is it. So we can use these to model in real time, and we're been doing this on and on. So it's a highly effective tool to use to fingerprint and to determine which compounds are coming from which facility. And you can use other options for odor analysis, besides ours, but this one seems to work the best for this really detailed fingerprinting analysis. If you have any questions, please feel free to reach out.
I'm looking at chat. There's a little bit of delay, so whether we have questions there. I mean, I think this is really interesting. It's fun to see these high-end mass spec systems. There's a couple of them that commercialization's increasing on, and putting them in a van adds a whole nother layer of usability. Significant project work to do, but it really does kind of show a future of the chemical analysis.
Yeah. This was just a small part. This was all through the Bay Area Air Quality Management District, and our part was just a small part of what Jacobs and several other companies were doing out there. But yeah, it was a huge characterization project that went on for a couple of years.
Okay, Steve, disconnect so we can get the next.
Yeah, Steve, disconnect, and Artavan, please start to share, and we'll see. Somebody asking Steve, what facility was the prime odor source overall?
It was the trash facility, the landfill.
Okay.
And actually, it was just one component of that landfill. It was the actual receiving area where all the trash was brought in fresh. I guess it's trash, but brought into the facility fresh. And they actually hand sorted a lot of this to get the recyclables out. And that was the biggest area, the biggest contributor to the actual odor there.
Thank you.